This is Kosmographia, the Randall Carlson podcast.
And welcome back, ladies and gentlemen, to the Kosmographia podcast with Randall Carlson. Once again, we are joined by everybody that you usually see. Bradley, how you doing this week, sir?
I'm a normal suspect here, or the usual suspect. I guess we'll let Mike be the normal suspect.
He's the
I'm
normal
good.
one, yeah.
I'm really good, though. We just had the first case in my county a couple days ago, so that was newsworthy. But everybody's still milling around, and it seems pretty normal around here.
Oh, that's good. Mike, how you doing, sir?
Everything's fine here. Thank you.
So everything's normal in your world, Mike?
Yes, everything is normal in normal world.
Good. We're right.
Very reassuring.
It's always comforting to know that.
Yeah.
That's right. We can all proceed comfortably.
Somewhere out there is normality.
Yeah, somewhere. I'm not sure where, but
Normal, of course, is a relative term. I'm just normal compared to you guys.
yeah, I realize that, Mike. There are other people in the world who are even more normal than you.
There you go.
No doubt. That's one of those words like reality that always has to be in quotes. Normal.
Next to whom, Mike, you would look positively abnormal.
I've been told that, yes.
So, hey, you know what would be fun? We got one of those people on the show sometime.
That might be interesting.
For a very short period, though.
So what, somebody
A very short period.
somebody really normal?
Yeah, I mean, yeah, not a faux normal like you, Mike, a real normal.
Right. The problem with that kind of normality is that it slowly degrades the longer they're on the show, right?
That's the point.
So if we bring them on the show, they start out like extremely normal, but the longer they're actually in the show, the less normal they become just by being here.
The more abnormal.
That's right. So we'd have to kick them out after 5 minutes, or else they'll lose their total normality. So
Yeah. So then collectively, we are the abnormals.
That's right. The normality around here is the abnormality. That's
right.
Mike is the weird one because he's normal. That's
I never thought of it that way.
Yeah.
I was just gonna say I've always said weird is different and different is good. But now you're calling normal guy weird, so yeah, I'm all thrown off.
I mean, he's weird compared to us because we're all abnormal and he's not, right?
Yeah, we're the transverse normal.
It's okay, Mike. We love you.
Yeah.
Please.
So I see what's behind Randall, but Brad, what is that behind you? What are you showing us here? Blue.
You're blue skying it?
Blue skying?
Well, no, these are compressed layers of ice.
Ah, okay.
So
makes sense now.
It looks like a painting.
I thought it was a painting of something.
No, stripes of blue. Yeah, it's actually annual layers of snow packed into ice on the
annual layers.
Sheet.
Okay.
Yep.
Right. And we've been talking about that. The ice sheet is a preservative environment for various kinds of proxies. Kyle, what is a proxy?
It is something that tells you that something else was there.
Yeah, well, I would say that kind of works.
I don't know the technical definition.
Well, it's kind of it's kind of like indirect evidence.
Okay,
right?
Yeah.
It's like indirect evidence. And when we look at, I always kind of like look at evidence in kind of two different forms. We have a microscopic and a macroscopic form. Macroscopic means it's something you can see. It's a big boulder laying on the landscape that doesn't belong there. It's a it might be an impact crater in the ground. It might be a cataract, or it could be any number of things, right? That's kind of like the footprints, because when you're doing forensic detective work, a footprint is something you see in the ground. A fingerprint, you don't see it without enhanced perceptual capabilities. You see, so we rely on technology to be able to see the fingerprints, but the fingerprints can be just as effective in figuring out what happened as the footprints. You got to do both, right? You need the microscopic and the macroscopic. So when we're talking about ice cores, now we're talking microscopic, right? For the most part. But in a lot of the layers, and I don't see any in this section that Brad's got here, although I'm wondering what this real light colored layer is right here. That stands out pretty distinct. I wonder, that couldn't possibly be volcanic ash, could it?
No, I read a little bit about it, but no, there wasn't any volcanoes mentioned.
Okay, so who knows what that is?
Yeah, what is that?
I just said I don't know what it is.
They may have it tunneled out so it's like a wall, so it might actually be some light coming in from the other side, and that's a less dense.
Maybe. Usually they extract it in cores. The cores are maybe 5 inches in diameter or so. So it could be that we're just looking at a very close up of the actual core rather than a slice.
No, this is like a wall. The other pictures have a person standing next to it, like it's a big 8 foot by 8 foot exposed section of the ice sheet. So they're deep underneath it.
Oh, so this is in situ.
Yes.
It's on the site. It's not. Okay, interesting.
Correct.
Okay.
Yep.
Couldn't tell from.
I did that on purpose.
You did that on purpose.
Because I wanted to have a core, but I ended up finding a whole wall full of it. So
Well, no, it's great because it really it sort of conveys the idea that you have these annual layers.
Exactly.
And you can actually count the annual layers. And sometimes even when they're not visible, they have electrical properties that will vary with the seasons that can actually be measured. Because, for example, in the spring, let's say, that's varves I'm thinking of, but in ice cores, let's say you have a period where it's more wind, right? Let's say you have a windy period, which could be the result of any number of things. Let's say it's because of the jet stream shifting, right? And if the jet stream shifts, so it's moving over the ice sheet, what's going to happen is the windier it is, the greater is going to be the particulate matter that's being carried, right? Makes perfect sense. So what in some of the ice cores, you can actually discern there will be dusty layers, which is indicative of more wind. Now, one of the things that seems to be interesting in the ice core layers that come right after the younger dryas boundary is the enhanced presence of dust, primarily in the form of calcite and silica, because this is material that's being blown off the continents. And that's the result of two things. This much enhanced presence of dust in the ice cores is, first of all, it's windier, and second of all, if the vegetation is gone, now you have greater erosion and exposure of the ground dries out. So, and what happens is in the aftermath of either some type of extreme climate change causing the existing vegetation canopy to die away, or in the context of what we've been talking about here, extreme widespread fires that essentially erase the vegetation from the landscape. So now you've got a barren landscape. And so not only is that landscape going to be more susceptible to erosion by water, and so if you have a lake there's a big fire, now this landscape is more susceptible to erosion because the vegetation has died off. The vegetation helps to protect the ground. It acts as almost a blanket protecting the ground. Vegetation is gone. It now rains. It begins to erode. So let's say there's a lake. The erosion goes into the creeks, into the rivers, the sediment that's created by the erosion. That is carried and dumped into lakes. So you can, by looking at the varved layers, which are actually the annual layers within a lake, right? All of a sudden, let's say you're looking at these little layers that are, a half a centimeter thick, which is the normal deposition into this standing body of water. And then all of a sudden, there's a layer that's 2 inches or 3 inches thick, right? So that's telling you something. It's telling you that, well, for whatever reason, there was a massive influx of sediment. Well, in order for there to be that massive influx of sediment, You've got to have some way of freeing up, which usually means you have eliminated the biological canopy that's holding everything in place. I mean, it's well known that if you take away, if you burn off a forest, it's going to become much more erosive. So the way you determine that is through the proxy. The proxy is you look at the layers. So you look at the layers in the ice, you can count annual layers. The dust in the ice, the ammonium. And see, look here. Now, here's where it gets convincing and much more than just speculative. For example, at the Younger Dryas boundary, what we learned is that there's enhanced deposition of both ammonium and nitrates. These are byproducts of biomass burning. So now you've got the layer with these big spikes of ammonium and nitrate. Now this is followed by a period of maybe a century or a couple of centuries where it's now a lot of dust. So you put 2 and 2 together, what's happened? Ammonium and the nitrate are expelled during large-scale forest fires, right? That's now followed by a dusty period. Well, that's telling you there was a big fire, it burned off the forest canopy, and now you've got barren land, and that barren land is now the wind is coming in and picking up the dust from that barren land, blowing it around up into the atmosphere, and a lot of it is settling out onto the Greenland ice sheet. So,
right. So I've got a different image here. I don't know if you're not looking at the gallery view, then this one's got the darker layer, so you can see more of the seasonal. This is from the Andes in Peru somewhere. So yeah, this is exposed above the ground, but yeah, you can see the dark layers much more readily in this image.
Now, normally, you will have, same thing like in a lake. Seasonally, spring, you're going to have much more runoff. So you'll have coarser sediment. It'll usually be darker, and you have these what are called the varve couplets in a lake. So you got this layer of sediment, of typically mud that forms on the bottom of the lake, and then at the bottom of it will be a darker and coarser, and then as you grade upwards, it becomes finer, and then it becomes lighter in color, and then you have another coarse layer. And so the coarse layer is spring, when a lot of stuff is being flushed in. And so you can go down and count the layers, and you can go back. If you take a core sample, you pull that up, might go back, you might have 1,000 layers in there. And then you can go in and you start looking at it, and you can, by looking at a pollen that's in there, you can know what was growing around the shores of that lake. Now, isn't that cool, right? So, you might see a major plant shift. Oh, and here's another thing. See, so if you're looking in the sedimentary cores, like after the Younger Dryas, you have this hiatus where everything is very, you have the ammonium and you have the nitrates, fire. Then you have the dust accumulating. That's the barren landscape, right? Now pollen starts showing up, right? Interestingly, the first type of pollen is ferns and spores as well, is from ferns, because ferns are the colonizer species. For example, Mount St. Helens, which Brad and I visited 3 or 4 years ago while we were going to waiting for Graham Hancock to come into Portland so we could rendezvous with him. We had an extra day, so we went up and we visited Mount St. Helens. And here you had this completely lunar landscape, which is now very interesting because it's in, in the successional stage of regreening. Yeah. Exactly. Yeah. But so one of the things noticed at Mount St. Helens is that the first plants that come back that begin to put down some roots, die off, and help contribute the materials that can become future soil are ferns, right? So they found a huge fern spike in the immediate aftermath of the Cretaceous Tertiary impact, right? Which was consistent with the idea that you had large areas of the planet, because they looked and it was geographically diversified, widespread. You have this evidence that there was barren land, and then you have fern spores showing up. Well, so the fern spores are basically the colonizer species that are coming in after the fact. So guess what? Came up right there in the centuries post Younger Dryas is fern spores, particularly in North America. So there you go. I mean, there's the whole sequence. Somebody, what possible other explanation you could come up with take each one of those individually alone, maybe you can't make a case, but you take the ammonium, the nitrate, there it is on the lower level, and then you've got the dust. Oh, but then right immediately after the ammonium and the nitrate, or right mingled in with it, you now have microspherules. You have magnetic grains. You might have nanodiamonds. So here, now what happens is each component that's added to this body of evidence makes the ultimate outcome more convincing. Each one almost has an exponential effect in terms of what it can do to eliminate competitive theories.
Right. And there's spikes in those things, right? Spikes in the magnetic grains and in the microspherules, because those are supposedly there's a certain amount of them all the time.
Yeah,
is that the idea?
Yeah, daily. There
right.
are usually they're referred to as cosmic spherules, and
cosmic spherules.
Yeah, they fall from the sky, or they can be volcanic, or they can be anthropogenic. They can be created as a byproduct of industrial processes. The point here, though, is that the ones that are created in the high energy environment of an impact are very distinct. And we'll look at some of that. In the next hour, we'll look at some of that. So, anyhow, so one of the studies we haven't talked about yet was a really cool study that came out back in 2012. Lead author was Ted E. Bunch, research team, and our buddy, there were 17 other authors of this paper. Our buddy George Howard was one of them. And it was published in the Proceedings of the National Academy of Sciences on July 10th of 2012. So in this study, which is entitled Very High Temperature Impact Melt Products as Evidence for Cosmic Airbursts and Impacts 12,900 years ago. Okay, there we have two things, two really important variations on these impact and these cosmic encounter events. The airburst and the actual impact. You see, they leave distinct signatures, yet one event might include both airbursts and actual impacts. Kyle, give me a good example of a airburst event that we might know about in recent history.
The Tunguska event.
Exactly. That was an airburst.
And what's the Chelyabinsk?
Chelyabinsk was airburst. Yeah, exactly. Now, of course, Chelyabinsk wasn't nearly as powerful as Tunguska. If it had been a Tunguska class bolide that came in back on February, whatever, I think it was 2014?
13.
Something like that. It was also way higher, right? It was 25
It was higher.
miles.
And one reason it was higher was because it was a smaller object. Right.
So bus sized.
Yeah. So, nobody was killed, but a lot of people actually were injured, and some of them pretty bad. And there was something like 1,500 buildings damaged.
Yeah.
It was equivalent to something like a 5-point something earthquake, I think.
Blew
windows.
Out a lot of glass windows. Yep.
Yeah. Windows blown out. Now, if that object, let's say here's the plan. If the objects are coming in, they can come in anywhere from perpendicular to the surface or oblique to the surface, right? So now, if it's coming in perpendicular, it's got less atmosphere to pass through, right? Compared if it's coming in at a low angle, oblique, right? So the atmosphere causes friction, which causes braking of the thing. The object is braking as it's coming. B-R-A-K-I-N-G, not B-R-E-A. Although it's doing that too. It's actually braking and braking. But if it's got that shorter pathway through the atmosphere, that increases the probabilities that it's going to penetrate all the way to the surface and impact the ground, right? Coming in at oblique, you might actually be passing through double the amount of atmosphere, so that reduces the probability of actually hitting the ground. The Tunguska object was a fairly low angle. From the eyewitness accounts, it does appear it was a low angle oblique entry into the atmosphere. Because for one thing, it was seen over quite a vast distance, which would be more consistent with it coming in like this than like this. See, A lot of the computer models for impact-related effects just generally start with the bolide coming in at 45 degrees. But in any case, if it comes through oblique, it's going to deposit a whole lot more of its energy in the atmosphere. And that's what Tunguska did. And basically, it's moving so fast, you got to figure it's moving 20 miles per second, right? So if it's moving at 20 miles per second, right, it's not even half a second from the time it first impinges the outer stratosphere to the time it would get to the surface of the Earth. Just a fraction of a second, see? Now, the atmosphere doesn't have time to get out of the way. So what does it do? It just compresses. And at some point, what'll happen, like unless, and this depends not only on the angle of entry, but also the density of the object. The denser the object, the more likely it is to survive that atmospheric passage. Tunguska would have been a low density, almost certainly part of a comet. And we'll get to that when we devote a whole several discussions to Tunguska, because it's fascinating stuff. And it's linked possibly with the Taurid meteor stream. But in any case, what it comes down to is if it's a lower density object, its survival through the atmosphere is going to be reduced, its probability of survival. A higher density object, if you're talking about an iron-rich meteorite, which is at the other end of the density spectrum, you got, say, a low density object, which is a comet nucleus, which is really only about a gram per cubic centimeter, or depending on the amount of material entrained within the comet nucleus can increase the density, but it's going to be towards the low end of the scale, close to that of ice. At the other end of the scale, you got a density that's closer to cast iron. And you got the whole range in between. Sort of in the middle, you've got the stony asteroids. So picture this. Here, if you have a ball of cast iron in one hand, a snowball in the other, and then a rock in the middle. That's kind of the range right there. That's one way you can think of it. Stony asteroids are going to be more disrupted by their passage through the atmosphere than iron asteroids, right? The things that are going to really survive, even small sizes, survive their passage through the atmosphere are the irons, the metallic asteroids. So the most vulnerable to disruption through atmospheric passage is going to be your Tunguska equivalent densities. The most likely to survive is going to be the irons. So it's the irons, and an important difference here, it's the irons that hit the ground, gouge out a crater that we can go and look at, right? So what's a good example, say, of a really well-known crater, say, in America? Kyle?
Meteor Crater or Behringer Crater?
Yeah, that's a good one. And so I am going to
I was just looking at pictures of the object that came in on it, or the pieces of it they found.
Pictures
there's a huge chunk of the metal that they mined out of the bottom of that thing.
Yeah,
in the little, like,
that's how you
visitor
know
center.
that it was an iron, because you pull out.
It's beautiful.
Yeah,
it's awesome.
It's not much bigger than a watermelon, and it weighs like 1,400 pounds or something.
No, I'm pretty sure from what I remember, it's that big.
So important difference now is what I'm talking about, is that the high density iron objects typically will survive their passage through the atmosphere to strike the ground, producing the crater, the classic crater shape. The lower density objects like Tunguska will not be so likely. Of course, as they get bigger, I mean, if you had a comet nucleus that is a mile in diameter, say, yeah, a bunch of that would survive passage. Would it fragment as it's coming in? Probably. Would it actually have started its fragmentation even before it arrived? Probably. But in any case, even the lower density objects, once they pass a certain size threshold, yeah, they will hit the Earth. But one of the things that's interesting to keep in mind about the contrast between Meteor Crater, also known as Behringer Crater, and the Tunguska object is that both of the two bolides were roughly, from all of the estimated sizes, were roughly the same size, about 150 feet in diameter. I think the Meteor Crater one was estimated to have been moving 20,000 miles per hour, somewhere like that. I think is about what it was when it made Earth contact. But the point is that the denser objects put holes in the ground, and that's macroscopic. That's your footprints, right? Let me move there it is.
It's kind of a grainy photo, but let's see, I got another tab here.
Yeah, but yeah, there it is. Yeah, I saw somebody, you can see right here, over here is where the visitor center is. And a couple of weeks ago, somebody posted a picture of Meteor Crater, and they were marveling at how close it actually came to the visitor center.
Jeez. Brilliant.
Okay, so
I think they were. I was reading about it. They said that it's called the Holsinger meteorite, is the largest piece that they found of the object that they think that made Meteor Crater.
Okay.
And they say that it's the largest discovered fragment of the 150-foot meteor that created Meteor Crater. So they think it was 150 feet across.
Yeah, that's pretty much that's kind of the dominant idea. About 150 feet, about the same size as Tunguska. But now here's
but it was metal, basically.
But it was metal, yes.
Yeah. So picture the Willamette meteorite. Is
that the right one?
There's no relative size guy, scale man next to that fragment, so I can't tell if Brad's probably remembers better. He has the best memory out of all of us.
Yeah, Brad knows. It was the size of a watermelon.
I was like, it's huge.
I got a couple pictures of it. That's how my memory works. I've got pictures of things.
So
anyway, yeah.
Well, there we go.
Okay,
that's pretty big.
He might have been thinking of Willamette meteorite.
Let's see what you're looking at.
It's a couple of feet across.
Yeah.
Oh, okay.
But Russ it's on his phone.
Yeah, sorry. I don't have control over the computer in front of us, so I was looking it up. But Kyle can pull it up.
Okay.
There's a guy putting his hand next to it. Yeah.
Well,
yeah. So I was right.
Not much bigger than a watermelon. Okay, 2 watermelons. Is that what you're saying now? Okay.
It's quite a bit bigger than 2 watermelons.
Yeah,
Here we go.
Pretty big.
Okay, so this is interesting insight into your guys' psychology. Kyle was thinking much bigger than it really was. Brad was thinking it was much smaller than it really was. So
no, I think I'm right on.
Kyle thought it was like 2 or 3 feet across.
There you go.
Look at that guy.
That's it.
Okay.
I was saying,
what kind of watermelons do you get, Brad? What kind of watermelons you got over there in Nashville?
Here we go. Look at this. Okay. That is cool. Yeah, look at that. So, yeah, we've been there a couple of times now. It's definitely worth a visit, because even as you're standing on the rim of this thing, looking down into this awesome, yawning hole in the ground, you got to realize that this is a baby.
I think most people are familiar with it, but it's, a kilometer across. So it's, over 3,000 feet across and about 600 feet deep.
Yeah. Yeah.
Are people allowed in the crater?
I think if you make the right arrangements, I think they
when I went
groups in, but you can't go in on your own. No, I think.
That's right. They only let us walk up to the edge or something. And I think you're right. They do give tours or I can't remember. I seem to remember that they told us they used to give tours down there, but then some crazy guy jumped down the mine shaft that's in the bottom.
Oh,
and so they stopped giving tours.
What is this? There's always got to be one idiot that ruins it for everybody else.
Yeah.
What is that? Man.
Hold my beer syndrome.
Yeah.
He lived.
Meteor Crater. Iron object hits the ground. And I want everybody to ponder this little statistic here. This sense of relative proportionality that I'm about to talk about here. Objects the size of Tunguska, the density of Tunguska, they might be the same size, 150 feet. This one hits the ground, leaves a big hole in the ground. We can come by 50,000 years later, look at the hole, find the pieces of the object, makes it pretty damn clear what it was, right? Over here, it blows up 5 or 6 miles up in the air, right? If it blows up over a forest, like in this case, about 825 square miles of old-growth taiga forest is just flattened, right? Because of this, the pressure wave coming down from above, literally, and then spreading out laterally. And that's why under the epicenter of Tunguska, like a ring around it, is a group of standing trees that have had their branches stripped off vertically from the vertical shear forces of this blast wave coming down. It then moves outward. So the trees on this side of the epicenter are pointing this way. The trees on this side are pointing this way. Pretty damn obvious to Kulik when he first arrived there in the late 1920s. Leonid Kulik, when he arrived there, he was the first scientist to make it there, right? So he was pretty damn impressed. I think I read his from his journal, his diary last episode, how unsettling it was to look that as far as the eye could see, this whole forest is just flattened, right? The magnitude of that blast is extremely impressive, right? So here's the thing, though. In the late 1920s, it was obvious. You go there now, it's not as obvious. Now, to the trained eye, knows what they're looking for. Yeah, you will find remnants of the forest that was blown down. You can actually find genetic anomalies in a lot of the plants that are post impact, right? You can find where there are very small microscopic spherules embedded in some of the trees that did survive because of the blast wave carrying these microscopic particles actually embedded them into the cambium of the tree. As the tree has grown, if you drill into the tree and you pull out a core that goes back to 1908, you can find that microscopic evidence, that fingerprint right there, see? But what would happen if you come back 1,000 years from now, or even another century or two? Guess what? You're not going to probably even know to even look to see if anything ever happened there, such as a bolide impact. Certainly 1,000 years or 2,000 or 3,000 years from now, people could be, living there. They could have huts. They could have villages. There might even be a city. Nobody's going to even know what happened there. So there's a whole class of cosmic encounters that don't leave the lasting footprints that I'm talking about, you see? And so when you try to derive the, statistical probabilities of impacts, a lot of them up to this point have been based on crater counting. Well, if you're only crater counting, you're missing this whole class of impact-related events, right? Now, when you begin to look at the ratios of, let's say, the dense objects to the low-density objects, these low-density objects, the ratio is like 10 to 1. So think about that for a minute. There could be, just that alone implies that there's probably way, way, way more Tunguska-type events than had been considered. And there are some that are looking at this that are going, yeah, let's see. The low density objects are much more abundant than the high density objects. So if we're looking at things that are, 150 up to say 1,000 feet in diameter, well, then the low density objects might not be leaving those obvious footprints in the ground that we can find thousands of years later. And then from that derive assessments of the probabilities of encounters. You see what I'm saying? So I think one of the important insights that we really need to be thinking about here is that, yeah, there may be a whole lot more of these encounters, Tunguska type encounters. And if there is, hey, that's important to figure into our planning, because a lot of the planning, particularly back in the post, 80s, 90s, even into the 2000s, the probabilities of impacts, if you look at how they're derived, a lot of them, if not most of them, are derived from crater counting. Now, the thing that Victor Klube and Bill Napier and Will Asher and those guys have been looking at for about 30 to 40 years. Let's see, I think Klube and Napier's first book that I read, Cosmic Serpent, came out in 1980. So that's 40 years ago, or maybe 81. So right in that very early 80s, right? Right around the time that the Alvarez team was discovering the iridium signature at the KT boundary, right? So in that book, and ever since, they have been amassing the evidence and making the argument that there might be times in history, there are certain epochs where Earth regularly encounters much greater density within some of the auspicious meteor streams, the clumps, you will, because all meteor streams ultimately come from the disintegration of comets, right? So if you got a comet, it's going around the sun, it's going in its orbit around the sun, and each time it's passing, let's say, the sun or passing nearby Jupiter, the gravity field literally begins to take it apart. Now it can be gravitationally induced fragmentation or just something, within the comet nucleus itself, because the comet nuclei are loaded with volatiles. So you might have major discharge and spalling events that happen even when it's not necessarily in the vicinity of Jupiter or the sun. But in any case, each passage around, it's discharging part of itself. And ultimately, it'll just keep discharging and discharging as it goes around until it's fragmented into dust, right? In that process, it'll form a dust stream. That dust stream will ultimately be swept up by the planets. If it's still in the form of a coherent nuclei, its chances of falling into the sun are pretty great. The sun is the big vacuum cleaner that sucks in a lot of these comets, and there's way more comets than anybody had realized that are falling into the sun every year. And this is something that became obvious once we had some of the solar observational satellites operational within the last 20 years. One of the unexpected discoveries was the number of sun-grazing comets that existed out there that nobody was seeing. And obviously one reason you don't see them is because they're you see them in the direction of the sun. And then otherwise, when they're out there in their pre-orbit, they're going to be really almost too small to detect. But there have been a regular succession of Halley-sized nuclei that have seen falling into the sun, right there when they're making their perihelion passage. Now, a Halley-sized nuclei is maybe 10 miles in diameter. So the whole point here is that what Klube and Napier were getting at is that there will be these episodes where a comet comes in and they actually begin to theorize the possibility of a giant comet nucleus that might have been 60 to 80 miles in diameter, making entry into the inner solar system and becoming Earth crossing somewhere between 25 and 30,000 years ago, right? And then it began to undergo a hierarchy of disintegrations. Well, it takes a long time. It takes multiple passages, multiple orbits for this material to get uniformly distributed around its orbit. So right now, the Earth passes through the Taurid meteor stream twice each year, once in late June or early July, and again, late October or early November. In fact, interestingly, the November Taurid meteor stream peaks right around Halloween and the couple of days after. It's for that reason they've often been referred to as the Halloween meteors. We're going to get into and looking at some of the very interesting connections, say, between the origins of Halloween and the correlation in time with the Taurid meteor stream, but that's for a later discussion. But in any case, the idea is that the material is not uniformly distributed throughout the orbit, so there are clumps, there are clusters. If it so happens that the Earth is passing through the stream when the clump is there, you have an enhanced probability of impact or encounter events. So one of the things that they then did was by studying, as a consequence of studying the architecture of and life cycle of comets, is they realized that there would be these epochs of enhanced impact probabilities, and that there actually may be times when Earth encounters a swarm of Tunguska-like objects, creating literally a cosmic storm of these things raining down upon the Earth. And let's say you have 100 Tunguska objects. Well, now you're talking about something that's going to be as devastating as an all-out thermonuclear war. Yet, 1,000 years later, what are you going to find other than microscopic evidence? And here's the thing, that microscopic evidence might be there just like with the Younger Dryas boundary layer. It's been there for decades and decades. It's been there for whatever, 13,000 years, right? But unless you go look for it, you're not going to know that it's there. I mean, when you walk into a room, are you going to think, you're thinking about, I wonder what the fingerprints are on that doorknob right there. Unless you're thinking about it and you have a reason to look, you're not going to see it. Now, the thing is, when Richard Firestone went and began to look at that Younger Dryas boundary, it was because he had a reason to. Because Vance Haynes had pointed out that at this boundary was where at 70 some sites where you had a boundary, or at least 50 some sites where you had a discernible boundary, well, you had megafauna below it, but not above it. You had Clovis culture below, but not above. So, and then when the Greenland ice cores started coming out in the early 90s, and you could correlate and go, look, right there at the Younger Dryas boundary, you have this massive spike. You have this massive warming spike followed by an equally rapid, almost plunge in global temperatures. So now you got megafaunal disappearance. You got you've got an abrupt climate shift, and you've got Clovis culture disappearance. Well, now you got a reason to go back and take a closer look. So Firestone went back and took a closer look, and that's when he started finding the impact proxies right there. So now he comes out, publishes a paper, causes a big stir in the scientific community, and then there's a group that looks at it and go, no, we can't, no, we've got this figured out. Human hunters took out the megafauna, right? It was climate change that, whatever, or it was climate change. Those were the two dominant ideas coming into the 21st century. It was human hunters, it was climate change. What they meant by climate change now was not a catastrophic climate change where you might have a drop of 7 or 8 or 10 degrees in a matter of weeks or a few months. It was a climate change that would have been stretched out over 1,000 years, causing, shifting vegetation patterns and whatever. When the spruce trees shifted north, somehow the mastodons weren't able to move as fast as the spruce trees to get, from lower latitude southern United States up to the Canadian border. And so they died out. I mean, basically, that's kind of the theory. As far as the last time I checked, elephants, I would think, could keep up with a shifting forest biome. But anyways.
Right, yeah. It seems like trees probably can't move as fast as something that can walk, right?
as a general rule.
Right, yeah, as a rule.
Yeah, as a rule. So those were the two competing theories. So when we say climate change, if I would say, yeah, climate change was clearly involved, but not a climate change that takes 1,000 years, a climate change that takes maybe a year or 2 years to shift from interglacial to glacial conditions and back again, right? Now that kind of a climate change, clearly it could knock out the forest, and then what happens to the whole chain, the whole food chain in that forest? Well, it's going to
collapses.
Yeah. So, but the thing is you've got climate change now. Okay, well, after Greenland ice cores, okay, so we've got these massive spasms of climate change around, at the Younger Dryas boundary transition. We've got massive, at the Younger Dryas. So at the beginning of the Younger Dryas, at the end of the Younger Dryas, right? At the end of the Younger Dryas, it's the YDB Younger Dryas pre-boreal, which is the name of the period that comes immediately after the Younger Dryas, just as the Alarod was the period that came just before the Younger Dryas. Then, of course, you have the Older Dryas, which we haven't talked about, which wasn't as severe, but it was followed by this 14,600-year warming spike, which I think was probably responsible for the first rapid sea level rise that was a consequence of the accelerated melting of the ice sheet. And then you had the Older Dryas, then you had this gradual warming, and then you had the Younger Dryas that interrupted the gradual warming that would have been the result of changing geometries between the Earth and the Sun. So this would have been a much more prolonged, slow, which had all the earmarks of being related to the Milankovitch ideas of global change, because this continually changing amount of radiation impinging upon the Earth, which is due to the changing orbital geometries. The orbital geometries were shifting, say, between 14 and 13,000 years ago, which would have implied that the planet was warming. And the evidence suggests that it was, because we see, boreal forest shifting north, deciduous forest following right after. We see the first major recession of the ice sheet, and it's becoming rather balmy, right? Now, all of a sudden, boom, at 12,900, that's interrupted. And within a matter of a year, like, boom, back into full glacial cold, right? So now we've got this massive climatic spasm that was recognized by 1992, 1993 after the JISP and GRIP ice expeditions extracted the 2 cores from the summit of Greenland. So then the question then becomes, well, okay, we could say that, you know, this contributed to this or that. It could have certainly could have contributed to the megafaunal extinctions. But here's the question: what caused that climate change? We can't just say, oh, the climate changes. It suddenly warmed up by 8 degrees centigrade within 5 years, without going, well, what is driving that change? See. So all of these factors kind of came together in the 2000s, and you know, some scientists began trying to look outside the box to think there must be other explanations. So, for example, one of the ideas was that I think that there was a nearby supernova or a galactic. Oh gosh, it was actually Firestone's first iteration of his idea. But then that evolved because once they took a look at the boundary layer, which in so many places, as Vance Haynes pointed out, had this black matte layer. So then when they went back, they took a closer look. That's when they began to find the proxies. So these proxies now they've been studying these, you know, for for 13 years now, since Firestone's first paper.
Since they published, right?
Yeah, since they published. So getting back to this paper from 2012, which was lead author was Ted Bunch on it. I think what we'll do is, before we get to that paper, we'll go ahead and we'll take a little break. Then when we come back, we'll jump into this paper.
Not a break or a break, but take a break.
We're going to break the continuity of this communication that we're doing here. That's, you know,
okay.
Well, when we say break, we're talking BREAK, right? We're going to take a break.
Yeah.
Right. And
we're not going to take a BRAKE.
By hitting the brakes on
hitting the brakes to take a break.
Okay, yeah. So we're going to hit the brakes to take a break.
That's right.
But we will be back.
We will be back.
Okay.
All right, ladies and gentlemen, welcome back. And I guess we're getting into the 2012 paper right off the bat.
Well, actually, I'm going to
take it away, Randall.
I'm going to jump back 3 years. Still a paper. Lead author is Ted Bunch, but this one he also wrote with Whitkey, West, Kennett, father, and Kennett's son. And it was in 2009. So this is, you know, pretty early on. It's, you know, a couple of years now after the seminal Firestone paper. And this was entitled "A Summary of Impact Markers and Potential Impact Mechanisms for the Younger Dryas Boundary Impact," or YDB. We're going to be using that a lot. YDB. So when you hear me say that, that's Younger Dryas Boundary. Okay, the YDB impact event at 12.9 Ka. Published in, it was a presentation at the fall meeting of the American Geophysical Union. So until the announcements of a possible impact event at the beginning, of the Younger Dryas, the impact layer that resulted from the Chicxulub impact at 65 million years ago was the only geological boundary known to contain coeval or simultaneous peaks in various impact markers, including diamonds. Here, we compare impact markers from the Cretaceous Tertiary boundary, the Younger Dryas boundary, and the 1908 Tunguska airburst layer. First order markers related to impact and biomass burning include, and here are the things now that we're looking for, right, and are being found: magnetic spherules, carbon spherules, nanodiamonds, both cubic and Lonsdaleite, which are differentiated by the pressures under which they are produced, and the fact that the cubic nanodiamonds are, just like it says, cubes, and the Lonsdaleite is hexagonal. iridium anomalies, charcoal, fullerenes. You know, these are the soccer ball shaped molecules, and they'll contain helium, and the ratios of the helium-3 to helium-4 ratios is a signature of a cosmic genesis. So you've got the fullerenes, which we have not really talked about yet, but we will. Grape-like soot and widespread extinctions. So he's throwing the extinctions into the mix. Now, extinctions could certainly be considered a macro scale, because you find the bones of these things. You know, you find the mammoth bones, you find the carcasses and the remains. You can find the dung, you know, of what animals were living in a cave at the time something happened, right? And from that dung, you can determine what they were eating, right? And once you determine what they were eating, then you know what kind of things were growing around there. Once you know what kind of things were growing around there, you know what kind of climate there was. See, so it's all this chain of logic, essentially. But what ultimately, it's very much like forensic detective work. Excuse me. We're looking at clues, trying to put these clues together to recreate the crime that happened. In this case, let's say that the crime is the murder of half this megafauna on the planet, the mass killing of the Clovis culture. Let's say, okay, these people disappeared. We don't know what happened to them. We got to figure it out, right? So we're on the track of this thing. Some people may think that it's figured out yet. It ain't. It ain't. We've still got quite a bit of work to do before we really figure out what happened. But anyways, they go on here talking about these things that are all kept, simultaneously here, the magnetic spherules, the carbon spherules, the nanodiamonds, the iridium, the charcoal, the fullerenes, the soot, which is the grape-like soot, is also called aciniform soot because it's like clusters. It looks almost like clusters of grapes, balls of soot that looks like clusters of grapes that form under these high-intensity wildfires, right? And then the extinctions. Observations and analytical data for the YDB are consistent with all of the KTB markers, while the last three markers are unknown or inconclusive in the Tunguska layer. But see, think about this now. Our studies, these rigorous and detailed studies that had occurred already on the KTB, the Cretaceous Tertiary boundary of 66 million years ago, that really were launched in 1980 on a new level. Here it is, 2007, right? So it's 27 years later, right? In that 27 years, we've learned a whole lot about the KT boundary and what happens during these great impacts. What we learned from the studying the KT boundary, without that, we probably wouldn't have really understood that there was something very similar or parallel that occurred at the Younger Dryas boundary. And so you're going to see that there's a lot of correlations between the two, right? Of course, part of the resistance to the YDB compared to the KTB is that, well, the KTB happened 66 million years ago. So it's sufficiently removed from history that one is not faced with the complicated challenge of somehow integrating an event of that scale and magnitude into historical models. And this is why the YDB event actually has a completely different significance, in that suddenly a cosmic event, a cosmic catastrophe, is brought right up to the threshold of human history. And it's kind of this wall between everything that has happened, say, in the last 10 or 11,000 years, and everything that happened in the 150 or 200,000 years of human prehistory that's on the other side of that wall. And that's why it's so important for us to really understand what happened, because I think by understanding really what happened at the Younger Dryas boundary in detail is when our vision will really be able to begin to penetrate. It'll begin to dissolve before our eyes, and we'll be able to peer through to the world that existed on the other side. So anyhow, now we've got the Tunguska. The Tunguska event, if that had not happened, also, we would have been deprived of a great deal of insight into the Younger Dryas boundary. And so there will be frequent references to the Tunguska event, because that was like in the 20th century. I would put that right at the top in terms of the importance or relevance of these varied cosmic lessons that have been portrayed for humanity, been portrayed for the eyes of science, and for human intelligence to decipher. So 1908, we're going to devote at least a couple of episodes to that and really getting into the details and the specifics. And here's the reason: as they say, the devil's in the details, and we're trying to rout out the devil here, aren't we? Isn't that kind of what we're doing? All right, come on. You're hiding around here. Come on out, expose yourself. We're going to expose you to the light of day. Now, of course, Mies van der Rohe, the architect, he turned it around and he said, God is in the details, and that was the fundamental slogan of his architecture, was that he was attempting to put God into the details of his handiwork. Whether it's God or the devil, it doesn't matter. It's the details. We got to get into the details, because without those details, our thinking is going to be sporadic. It's going to be diffuse. It's going to be all over the place. But when we get into the details, so Tunguska event of 1908 provides us with a lot of details that we can measure. And luckily, we got there and have done the studies, while there's still something there to study. What'll happen is, as nature reclaims that, that region there, it's going to get harder and harder to discern the imprints of that event. So anyways, he's saying here that that observations and analytical data for the YDB are consistent with all of the KTB markers, and a lot of consistency between that and Tunguska, but 3 of them are missing. Selected markers for cratering events, for example, the Chicxulub, are: 1, a visible crater, shocked minerals, right? Particularly, you can think of shocked quartz here. What happens in the tremendous pressure of this impact? If it's a quartz-based rock, that quartz has very distinct fracture lines in it that make it's called a Widman-Statten pattern, and it's a series of cross lines. I'll have pictures of it that we can look at to really get the picture. But it's an imprint of a shock wave moving through a quartz-based rock. Impact breccia. So impact, that's really just all that is broken rock. When you have an impact, boom, you break up a whole bunch of rock. It gets thrown up in the air. It falls back down. Some of it falls outside the crater. Some of it falls back in the crater, right? But basically, you're going to have a big mass of broken rock, and it can be of all different sizes. And then you have microtektites. And microtektites now is in the tremendous heat and pressure of the impact. You have this material blowing off that's basically liquefied, and it's a mix of both the composition of the impactor and the composition of the target material. It all gets mixed together in the plume, thrown up into the atmosphere, and then it rains back out. And as it falls back to Earth, you can have macroscale tektites or microscale tektites. Microscale tektites we call microtektites because they only show up, obviously, under a microscope. Now, a macroscale tektite might be 2 or 3 or 4 inches long. You can hold it in your hand. You can feel it has weight and mass, and you can look at it, right? Now, as this molten material is falling back to Earth, it assumes a variety of aerodynamic shapes. And so the same shapes that you can see in the macrotektites that you can hold in your hand, you also see in the microtektites. So, again, all of these things are part of the pieces of the puzzle that we put together to try to recreate the event. So then let's jump down to the 2012 bunch paper and see where they go with this, because now it's like 4 years later, additional research. So, okay. There we go. So this is what they said. Now the team has grown. There's 17 others besides Ted Bunch, right? Very high temperature impact melt products as evidence for cosmic airbursts and impacts 12,900 years ago. So impact melt products as evidence for, and we talked about before the breaks, I want to get just that you're aware of that they're talking about both airbursts and impacts. And what is appearing more and more likely based upon the diverse nature of the impact proxies is that you had to really almost invoke both processes to account for the full range of proxies, if that makes sense. They say it has been proposed that fragments of an asteroid or comet impacted Earth, deposited silica and iron-rich microspherules and other proxies across several continents and triggered the Younger Dryas cooling episode 12,900 years ago. Although many independent groups have confirmed the impact evidence, the hypothesis remains controversial because some groups have failed to do so. And of course, we did talk about those. We didn't cover everything, but we looked at it. There were several important, actually, inconsistencies that the critics made that we didn't even address, actually. Might be interesting at some point to come back to that and scope out the full range of, the claims by the Firestone side, the attacks by the critics, and then the response of the Comet group and how they basically demonstrated the flaws and insufficiencies in the critics' attempts to rebut the idea of a comet impacting the Earth. So in this case, this team examined sediment sequences from 18 Younger Dryas boundary sites across 3 continents, North America, Europe, and Asia, spanning 12,000 kilometers, right, around nearly 1/3 of the planet. And what did they find? They found that all sites display abundant microspherules in the YDB, with none or few above and below. In addition, 3 sites, Abu Huraira in Syria, which we've discussed somewhat, Melrose, Pennsylvania, and Blackwell, South Carolina, display vesicular, high-temperature, siliceous, meaning a lot of silica, scoria-like objects, or SLOs, that match the spherules geochemically. I'll show you some pictures of these high-temperature vesicular. What does vesicular mean? It's got pores in it, right? Like Swiss cheese. Vessels, vesicular. Okay. The discovery of anomalous materials in a thin sedimentary layer up to a few centimeters thick and broadly distributed across several continents led Firestone et al. To propose that a cosmic impact occurred at 12.9 kilo annum. So kilo annum basically is 1,000 years. That's where we get the abbreviation Ka. So whenever you see Ka, it means 1,000 years. 12.9 Ka means 12.9 kilo annum, or 12.9 thousand years ago. Near the onset of the Younger Dryas boundary layer, which often occurs directly beneath an organic rich layer referred to as a black mat that is distributed widely over North America and parts of South America, Europe, and Syria. The YDB layer contains elevated abundances of iron and silica microspherules that are interpreted to have originated by cosmic impact because of their unique properties. Other markers include sediment and magnetic grains with elevated iridium concentrations and exotic carbon forms, such as nanodiamonds, glass-like carbon, aciniform soot, remember that's the grape-like clusters, fullerenes, carbon onions, where you have layers of carbon that are literally, a succession of layers, just literally like an onion, and carbon spherules. They then say that, and we got into this when we were talking about the work of Pequet, was that his name? We couldn't quite figure out, Patiev, we couldn't quite figure out how to pronounce his name, who did the work on the Greenland ice cores and found the, as they're going on here and explaining, the Greenland ice sheet also contains high concentrations of atmospheric ammonium and nitrates at 12.9 Ka, indicative of biomass burning at the YD onset, and or high temperature impact-related chemical synthesis. Although these proxies are not unique to the YDB layer, the combined assemblage, and here's the critical thing, it's the combined assemblage, is highly unusual because these YDB markers are typically present in abundances that are substantially above background. And the assemblage serves as a datum layer for the YD onset at 12.9 Ka. The wide range of proxies is considered here to represent evidence for a cosmic impact that caused airbursts / impacts across several continents. And then they have in parentheses, the YDB event may have produced ground impacts and atmospheric airbursts. So I am now going to do a quick square share screen so that we can see some of the things that they're talking about here, what they actually look like. So we'll do share screen. Here we go. Share.
All right, we see that.
Cool. So on the top row, we have those scoria-like objects, the SLOs that are found. And on the bottom, we have 3 examples of microspherules. On the left is one from Abu Huraira in Syria. In the middle is Blackville, South Carolina. And on the right is the one found in Melrose, Pennsylvania. Brad, you're spent a lot of time in Pennsylvania. Do you know where Melrose is? I did look it up on the map.
Not right off. It's probably eastern Pennsylvania, but yeah.
It was during the glacial maximum, say 15 to 20,000 years ago. What I do remember as I looked at it, it was under the ice sheet. Now at 13,000 years ago, the ice had probably receded far enough north that it was not under the ice sheet anymore. Might have to check with the residents of Melrose and ask them if they remember whether their town was under the ice sheet or not. 13.
That one on the lower right looks like, is that a smaller sphere on it or a crater?
Yeah,
right
from this I can't tell, but it could be.
I can't either.
You do actually find that, if we have enough time, we'll be looking at some pictures of those. If not, we'll carry over into the next episode. But you have places where, yes, the microspherules have craters in them from being hit by other microspherules. They also have sometimes where microspherules will be welded together because
like that middle one.
Yeah, exactly. Exactly, right there. Yeah,
embedded within the other one.
Yeah, and look, you can see these smaller microspherules that have become welded to the larger one.
Yeah,
it's exactly.
I'm going to call that one on the right the death spheral.
It looks like that, doesn't it?
Yeah.
That's no moon.
So the vesicular, is that the upper left one? Is that kind of the air
all
pockets
of these.
or gas pockets?
Yes, all of these are vesicular. A, B, and M are vesiculars.
Right.
They're the slows, the scoria-like objects. So these things, see, the point is these things are found in association with each other. And the scoria-like objects show evidence of having basically been melted and then re-solidify out of melt. Here's, as it says, the site graphs for these same 3 sites.
Sorry.
Not necessarily.
Right. Okay.
Okay. Site graphs for 3 key sites, the SLOs, which is the blue, right? The blue graph. And then the microspherules are the red graph. So the blue bar, horizontal blue bar, is the younger Dryas. 0, what is shown as 0 on these graphs is right at the YDB. I guess that would be right where they've zeroed out is where the platinum layer. They use the platinum layer that we talked about last week as the datum, right? So, I mean, you can see very clearly here how much they spike. So here, look at the middle one, the one from Syria. Here, the blue, see, this is the surface. So you're going down. So the deeper you get, the older you get, right? So as you go down, the amount of the numbers way down here close to zero, probably, I'm guessing, let's see, parts per million. I'm pretty sure it would be parts per million. And then you see right here what happens. Boom. The microspherules just spike way up. Same over here at Melrose, Pennsylvania. You've got this big spike of microspherules, and then you've also got these scoria-like objects that are basically peaking right at the same time. Same here, right at the same time. If you look at the peak here, here's the scoria-like objects here, here's the microspherule. So they're peaking simultaneously, and they're found right together, right? So that's a pretty good indication that whatever process created one created the other, right? So in looking for an interpretation of this, you have to come up with something that can not only put the microspherules there, but can also put the scoria-like objects. So we will escape from that. Then as we go on here, they're talking about another proxy, which is the melted silica glass. So I'm going to go ahead and stop the share for a second here. And the melted silica glass, they're basically...
You're also talking about several thousand miles away, right? Syria from South Carolina or Pennsylvania.
Yes, yes.
Probably 2,500 miles, 3,000 miles.
Exactly. So that raises interesting questions.
Yeah.
There could be two explanations that immediately come to mind. One would be that this fine-grained microscopic stuff is being transported through the atmosphere. It's being distributed, high up in the atmosphere, maybe even stratospherically, being carried around the globe and then deposited. Okay, that's one possibility. The other possibility is that there were airbursts in the vicinity of Syria.
Right.
And I don't think nobody has come to that conclusion yet. So there's a word. Let me see if I can remember how to pronounce it.
No, I think they have. I think that's what the village that they found was scorched. So there was an airburst nearby.
Yes, and we even talked about that. We did, didn't we? Although we should come back to that because I think we just brushed on it. I don't think we really looked at the details.
No, we haven't dug into that. So yeah, we'll get back to that one. Sorry.
Oh man, yeah.
But
sure.
The distance from South Carolina to Syria is 6,313 miles.
Bam, double time. Okay, I'm thinking small again.
Yeah, Brad, we got to cure you.
You gotta think bigger, Brad. What's wrong with you?
Yeah. Listen, Mike, I know for years you've been telling me I need to think bigger. Maybe now you need to focus on Brad a little bit more.
Brad with it.
Okay, now this is a word I have known how to pronounce it. I don't say the problem is you get a word like this and you don't say it all the time. You kind of forget, but it's La Chatelle Liarite. I think that's pretty close. La Chatelle Liarite, which is a melt glass product, right? You can actually, if you go, Kyle, to put the word in and then say pronunciation, we'll get the pronunciation. And this is how you spell the word. Lech. Lech. Are you on this, Kyle?
A little more difficult than Palace.
Lechatelierite.
I think that's
however you pronounce it
was made out of.
It is occur as a product of impact events, nuclear detonations, and lightning strikes. The Ted Bunch team that wrote this article that I'm still quoting from, we observed it in spherules and SLOs from Abu Huraira, Blackville, and Melrose, suggesting an origin by one of those causes. Lachatellierite is found in material from Meteor Crater, Houghton Crater, the Australasian Tektite Field, Dakela Oasis, and the Libyan Desert Glass Field, having been produced from whole rock melting of quartzite, sandstones, quartz-rich igneous and metamorphic rocks, and lust-like material. Now think about that. It's so hot, it's melting quartz. That's pretty damn hot. The consensus is that melting begins above 1700 degrees centigrade and proceeds to temperatures greater than 2200 degrees centigrade, which is the boiling point of quartz. That's pretty warm, I would say. If it's hot enough to melt and then boil quartz. Okay.
Bring your quartz to a boil.
What?
Yeah. Bring the quartz to a boil.
Yes, bring the quartz to a boil. This is one of the significant processes of the cosmic alchemy we're talking about here. So 2200 degrees centigrade, the boiling point of quartz. And all this has to happen within a time span of a few seconds, depending on the magnitude of the event. These temperatures restrict potential formation processes because they are far higher than peak temperatures observed in magmatic eruptions, that is volcanic eruptions, which are less than 1300 degrees centigrade, wildfires, which are less than 1454 degrees centigrade, fired soils, which are less than 1500, glassy slag from natural biomass combustion, less than 1290 degrees, coal seam fires, 1,650. So all of the known processes that could produce really high temperatures, they're not high enough. You got to get up to, like it says, more than 2,200 degrees centigrade to boil quartz, right? So what they're seeing here is temperatures hot enough to boil quartz. So that's pretty damn hot. So now you got to throw that into the mix, right? It's not just a matter of the microspherules and the magnetic grains and things. You now got this, how do we say
Le Chatelairite.
Le Chatelairite. Le Chatelairite. Okay.
Yeah.
Le Chatelairite.
Le Chatelairite.
Le Chatelairite. Yes.
Yeah.
Where's my monocle?
It's weird. It's really
We got to wrap it up here, Randall, by the way.
Oh, it's just getting interesting.
I know, man. I'm sorry.
It's Brad's fault.
Let him roll.
I know. Well, we will. Okay, so we know right where we're going to pick up next episode. We're going to be looking at high magnified images of SLOs. We'll be seeing what the La Chatelairite looks like. We'll be looking at from Abu Herrera. We'll be looking at from the Blackville, South Carolina, and we'll be looking at the Melrose, Pennsylvania. And we will see some very interesting imagery of, these high magnified stuff that's there, right there at the YDB boundary. What we're doing is we're taking that YDB boundary and we're just blowing this up where we can now look even into the nanoscale. And what we find there is pretty damn interesting. And then we'll compare that, for example, to some tektites. We'll look at the more spherules. We'll look at some pictures of spherules from Mexico, other places, and then we will look at some of the other things like the Libyan desert glass for comparison. We'll compare that to the La Chatelairite and the inner texture, the architecture of that stuff when you look at it really, really close, really, really fine.
I'd also like to see some comparisons to the YDB proxies to the KT proxies to see if we can get some pictures of that. That would be cool.
Yeah, I think I could pull some of that up. I don't know if I have it. Yeah, I do. I have that. We can definitely see that. We'll also look at some of the examples of the trinitite, which is the stuff that was created in the Trinity plutonium atomic bomb test, the first atomic bomb test at Alamogordo, because the high pressure and high heat of that created stuff that now also can be understood as an analog for cosmic impact proxies. So we'll look at some of that. Pretty interesting stuff. The desert glass, looking at some of the desert glass. We'll have pictures of some of the Libyan desert glass. And then, and then we'll go back into other, looking at some of the microtektites, which are pretty cool. And then we'll make an interesting connection with something we've already talked about, because in some of the cases that we're looking at here, when you look at where did some of these things come from? See, that becomes the next question. When you pull out and you look at a microspherules or an SLO or whatever it might be, you got to go, okay, was this produced locally or was it produced from somewhere else? But if from somewhere else, where? Because clearly this scale of stuff is going to be transported. It is going to be transported in the atmosphere. So you're going to have a wide distribution of this stuff. So one of the key challenges when you're looking at this stuff is determining, just like when you're looking at volcanic ash, you find a deposit of volcanic ash and you go, okay, where did this come from? What volcano did this come from? Well, every volcano has its own unique geochemical signature. And depending on where you would have an impact, the geochemical signature of the proxy byproducts is going to be unique. So the key there is in correlating, looking at that chemical structure of the magnetic grain or the microspherules and figuring out what is it consistent with. So that's what we're going to look at when we're going to actually find what I think are some hypothetical locations that have not yet been addressed by the scientists that I know of that are looking at this, but something we've already actually touched upon in a previous episode. So we'll come back to that.
Awesome, man.
That sounds great.
Extraordinary.
Hypothetical locations.
Yeah.
For sure.
So are you coming up with a Fahrenheit for us, Kyle, on 2200 centigrade?
Really hot. No, was I supposed to do that?
No, I just think
Really
you took
hot
that upon
Fahrenheit.
yourself earlier, and it's like, well, yeah, everybody's wondering, well, how freaking Fahrenheit hot is that? No, that's all right.
Yeah, I didn't do that.
We'll know
sorry.
next time.
Well, it's
Melting quartz, boiling
What
quartz.
I want to know, the last thing I want to know before we end this show is your restaurant. Are you guys going to have YD burgers and carbon onion rings?
No, probably not. But we are going to have Mastodon chili.
Oh man, that's
We're going to have half-pound mammoth burgers.
Yeah, YD
with
burgers.
cheese.
Come on.
Yeah,
There you go. YD burgers. Yeah.
we are
4,000
Yeah, we are.
degrees. 4,000 degrees Fahrenheit. 3992.
Yeah, 3992. That's pretty
All
damn high. Yeah, basically 4,000. And remember, it's greater than 22.
Right.
Yeah.
So yeah, we're
Mammoth
talking
burgers.
4,000 and up degrees Fahrenheit. So
Cooking.
I can confidently assume that any of us here or any of our listeners would not last long in 4,000 degrees Fahrenheit.
I don't think so. Yep. I believe that would reach my boiling point.
You
Yeah,
cook
no,
that burger in
interesting.
half a second.
Interestingly, I think the temperature, and I'm pretty sure it was Fahrenheit. I looked it up in the studies recently. I think right at the epicenter of the Tunguska explosion, it was estimated to be 10,000 degrees Fahrenheit.
Oof. That's up there.
That's up there, and I'll double check that. If it was centigrade, woo, that's really up there.
Yeah, that's like solar temperature.
Yeah, it is. Right,
Yeah,
it
you're
is.
looking
It is.
solar corona there. Yeah.
Exactly. You're talking that these events can actually produce temperatures that are like on the scale of the sun.
Man.
If you're wrong about that, there will be a correction in the comments section down below.
About what?
The temperature.
Oh,
Yeah. Someone will be like, he's totally
Down there,
wrong."
there will be a correction.
that's
Just
absolutely
look.
great.
Yeah.
Listen, I don't claim to
Fact
know
checkers.
everything,
Just almost everything.
right? Just almost everything. No, within my limited scope of awareness, I know a fair amount, but God, there's far more things than I don't know than I do know.
Scary.
I
That's-
think
I think that's
I think that's that's a pretty obvious conclusion to draw.
I was also thinking about, I've been thinking about the details thing. You're saying that the devil's in the details, God's in the details. And I was like, when you're talking about architecture,
Mhm.
God is in the details of the design. The
Yeah.
devil's in the details of the implementation.
Okay.
That's how I see it. God's in the details of the design. When you try to build it, that's where the devil shows up.
Yeah. Okay. I like that. I do. I like that. But
All
you know,
right.
when we finally get into like really getting into the traditional interpretations of some of these cosmic events, the devil will show up.
Yes.
Of course, at that point, we'll point out that the devil originally was nothing but a symbol
Right.
for a natural process. And only later was it anthropomorphized into this thing that we think of as the devil today.
And just to clarify, the melting point of quartz in Fahrenheit is about 3,000.
The boiling point is what we were looking at, I think, right?
Well, I don't know, boiling point, melting point, but the melting point is 3,000.
Okay.
Well, we just found out, we learned that the boiling point was 2,200 degrees centigrade, which is 3,992 degrees Fahrenheit. So
yeah,
melting maybe is going to be a lower temperature than actually boiling it, right?
Yeah, boiling is turning it into a gas, right? That's the idea.
Point taken.
We're talking about boiling quartz here, Mike. Not just
It's like the difference.
Just trying to help. Just trying to help here, guys.
No, but that's a good. So it melts at, what was the temperature again? Just right at 3,000.
Right about 3,000.
Okay, that's easy to remember. So it begins. Well, it's just like, take an ice cube out. You can. It's going to melt at room temperature, but it's not going to boil.
Right.
So. Okay, well, I guess that's that, huh? It's a wrap.
That's a wrap.
Woo.
We will be back to continue this story unfolding, and we've got so much more to dive into.
There is a lot
more.
more.
By too fast.
Yeah,
Brad, you got updates on the video channel?
Oh, nothing really new. Just briefly that everything should be there in sequence now. And again, there's a tip jar for instant donations on the channel banner. And again, it's me commenting, BY signature, not Randall yet. So just reiterate what we said last week.
Right. And people can get a hold of us, Kosmographia1618@gmail.com. Find the website, Kosmographia.com. RandallCarlson.com is coming. I know we keep saying that, but it is coming.
So good.
It's on its way. And I have to say, what I've seen so far, literally, look here. See, look. I don't know if you can see.
What the heck?
See that barefoot? That's because earlier when I looked, it literally knocked my socks off. So
it is an awesome website. It will knock your socks off. All the links are in the show notes. Anybody who wants to join us in the Scablands in September, please go find the links in the show notes and go send Darren an email at the contact at the cabin website.
Do we have time for Brad to quickly mention a more modest scale trip that we're thinking about and developing?
Sure.
Itinerary for?
We can always take an extra few minutes. But we're talking about several different ones in the southeast around our homes near Atlanta and Tennessee and North Carolina. So there's one into northeast Alabama we're looking at that would be for potentially 5 days, including travel, 4 overnights, go to some different mound structures, go to some geologic sites, go explore some caves and caverns, some cataract waterfalls. It's really rich geologic territory in our corner of the country here. So
really
doing some local stuff and just get some people out, seeing what's in the neighborhood and across the country.
Exactly.
But we're gonna do a big Scabland one or multiple Scablands one at the end of the late summer into fall and going into years ahead. But we want to do some locally where we are too.
Right. And so for people that are interested in those, they need to wait for the website, or is there a way that should they just tell us now or wait for the website?
I mean, no reason not to tell us if they're interested in that. And then,
we're going to activate some new email addresses linked to the new website where people can request those things specifically to be part of tours.
Okay.
Right. And just as a hint, as the quality of what's coming, if you see some of the recent thumbnail graphics that we've had for the podcast for the last several, big upgrade and, really cool looking graphics. So that's a little hint at where we're going with the website.
Mm-hmm.
That's right. All right, guys. Excellent show. Can't wait to do it again next week, as always.
I know, me too. I'm actually having fun.
Yeah, it's been a lot of fun. Thanks so much.
You know, I've always been a firm believer and advocate in the principle that when you're immersed in the study of the end of the world, you should have fun.
Yes, completely agree. Yeah.
Smile to the
All
end.
right, guys. Good night.
Good night.
Good night.
Ciao.